Queries and keys determine the attention weights. Value vectors are what those weights mix and move into the output. Take the sentence, the hungry dog chased the ball because it was tired. At it, causal self-attention scores every unmasked position through the current token. Hungry, dog, and ball are just 3 earlier examples. Their values can move information into the output. Watch the roles separate. Query and key scores change the thickness of the arrows into it. The dog might receive a large weight, the ball a smaller one, and hungry another useful clue. Those weights are routing numbers, not the payload itself. Now imagine each candidate carrying a small colored packet. The weight is how much of that packet gets through. Attention does not copy one whole word by default. It forms one output by taking a weighted mixture of the candidate value vectors. If dog gets weight 0.6, ball gets 0.3, and hungry gets 0.1, the output is 60% of the dog value, 30% of the ball value, and 10% of the hungry value, added component by component. Here is a transparent toy calculation. Let the 3 value vectors be dog equals 1, 0, ball equals 0, 2, and hungry equals 1, 1, with weights 0.6, 0.3, 0.1. The first output component is 0.6 times 1 plus 0.3 times 0 plus 0.1 times 1.7. The second component is 0.6 times 0 plus 0.3 times 2 plus 0.1 times 1, 0.7 again. So the mixed output is 0.7. Nothing mysterious moved as a word. Numbers were combined according to the weights. Only now does the compact notation become useful. Attention of Q, K, and V is softmax of the query key scores divided by the square root of key width multiplied by V. The final multiplication is the weighted value mixture we just built. In matrix form, QK transpose produces a score for every query key pair. Softmax turns each row into weights that sum to 1. Multiplying that weight matrix by V creates an output row for every query position. Focus on one row. The query at it compares with all the keys, producing one distribution across the available values. Change Q or K and the distribution changes. Hold them fixed and the value vectors are the things being mixed. A value vector is not a dictionary definition of a word. The model learns projection matrices that turn hidden states into values useful for the current layer and head. A coordinate might carry a feature, but we should not label it dog meaning or hungry meaning without evidence. That is why the same token can contribute different value vectors in different contexts. The input hidden state already reflects context, and the learned value projection transforms that contextual state into information this attention head can pass along. A useful mental model is routing plus payload. Queries and keys decide where to look. Values decide what representation arrives from each place. The output is a new representation, not a pasted word and not a human-readable definition. Return to the square root detail from the previous video. Dividing the query key scores by square root of d sub k changes the softmax weights. It does not divide, rescale, or edit the value vectors. With raw scores 16, 8, 0, the largest weight is almost 1. After dividing by 8, the scores 2, 1, 0 spread probability across all 3 candidates. The values can stay identical while the mixture proportions change. See the same 3 value packets below both distributions. The left mixture is dominated by the first packet. The right mixture combines all 3 more visibly. Scaling changes how much moves, not what each value vector is. One caution matters. An attention heat map shows weights, but weights alone are not a complete explanation of model behavior. The values, later linear layers, residual connections, normalization, and other heads all affect the final representation. 2 models could show similar attention weights while carrying different value content. Or a small weight could still matter if its value has a strong feature. Reading an arrow without reading the payload can mislead you. So do not say attention moved the word dog into it as if a token were copied intact. Say that the query key pattern selected a weighted combination of learned value representations, which then entered the next computation. In a multi-head layer, different heads can make different query key comparisons and different value mixtures. Their outputs are concatenated, then an output projection combines those head channels. That is useful context, but the core routing versus payload split stays the same. Here is the complete path. Hidden states produce queries, keys, and values. Query key scores become normalized attention weights. Those weights multiply the value vectors and add them into each output position. For the dog sentence, the it query can assign weights across dog, ball, and hungry. The weighted sum does not prove a single word was selected. It produces a context-dependent vector for the next layer to use. Remember the 3 distinctions. Queries and keys determine where attention looks. Values are the learned representations being mixed. Scaling changes the weights, and an attention map by itself cannot explain everything the model computes. That is what attention actually moves, not words as intact objects, but weighted value representations. The previous video explained why the scores are scaled. This sequel followed those weights to their payload.